Now on the outside section of an AC system, you'll see something familiar from the inside section. You're going to find your low voltage wires. And again, we have Y for the compressor contactor, O for the reversing valve, W for heat, but this is going to be a callback inside the heat. R is your constant 24 again, and there's our fancy common. Finding it again in another section of the system. Now earlier today, we had some students out here that they found a defrost board issue, so we actually took a defrost board that does not belong on this brand and wired it in. So we currently have 240 volts present, so I'm going to just go ahead and start from there. We're going to talk about what comes in and what runs and what doesn't. This thing, and I'll kill power to do some other stuff. So, first and foremost, our 240 volts is going to also come from a breaker. We're going to see 240 volts applied. Now, this is a contactor, and if you'll notice, we have 240 down here, but nothing across it at the top. And that's due to the fact that the contactor is not in. Now, if I take this wire right here and plug it in, I'll have 240 volts at the top as well, and 240 volts at the bottom. Another thing that we were just talking about inside was an open switch will read line voltage. Well, here we go. So we're going to have voltage, or at least read voltage here. Now watch what happens when I take it away. It's going to go back to 0. Open it, you're going to see voltage again. This isn't going to read exactly line voltage because it's a double pole relay, which means that there's no pathway for the full 120 volts to get all the way around the circuit. But we still have some other voltage down here, so it'll work. Anyways, and again, same thing here. Open switch reads voltage, closed switch reads nothing. So now let's say that we did come out here though, and we don't have power on. We come to it, we don't read anything at the line voltage. Well, it's simple. We're just going to go back to the disconnect and identify at the disconnect if that's where our power is. Now, if you work for a company that's also an electrical contractor, you can go past that disconnect. But if we only work at a company that has an HVAC license and the HVAC license is all, then that's the limitation. You stop at disconnect and you cannot go any deeper. You have to call an electrician out and allow them to come work on the unit. Luckily, I worked in an HVAC company that was both a plumbing contractor and an electrical contractor. So I was able to go and track those down all the way down to the power panel. But what we need here between, this is our contactor, these are the line voltage connections, and just like the relay we talked about earlier, the relay, its job is just to relay voltage across it. So what we would find here, if this thing's supposed to be running, is 24 volts from this side to the common side. So this is going to be our Y coming in and 24 volts out. Right now I don't have a call, I don't have the inside unit on, but 24 volts present, we'll pull that contactor in and let the unit run. If we do not find 24 volts there, that's when we're going to come back to our board and take a look and see what may have happened to cause that not to work. Now on this specific board, we're going to have a couple things tied in. One is our pressure switch system. So fastest and easiest move I find to do pressure switches, which I don't have out on this example, I wasn't doing refrigerant today, is I take off the service valves and I hook my gauges up. If they read 0, your pressure switch is open on low pressure. That's a lot faster than trying to go and track down wires and look everywhere else. Just keep it simple and look for the pressure. Is there pressure? If there's pressure, then that switch should be closed. If it's not, we'll find out here in a minute. But like I said, if there is no pressure in the line, then that's the reason the unit's not running. And you just go ahead and go from there. All right, so R is what gives this thing its logic. This little board here, it's only got a time delay and a defrost control in it. There's not really a whole lot going on. It looks like a whole lot, but it's not. So the time delay right here, and it's going to get it works off the R logic. So as soon as R comes out, 24 volt R circuit comes out, R in common, they start the logic on that time delay. There's a 5-minute delay. So the reason for that is it's called an anti-short cycle delay. It powers to drop to the building, to the house, to the neighborhood. When power drops and comes back on, we don't want this contactor clicking on and off like that. We want it to wait and then click in. We don't want power to continue to drop for the area that we're in. So what it does, we give it this 5-minute anti-short cycle delay. That allows the grid to kind of get juiced back up and everything to get running again, and then the contactor is going to come on and pull its high amp draw and start running. But what we don't want is the compressor to kick in for a minute, kick out for a minute, kick back in for a minute, kick out for a minute. That'll cause massive issues inside the compressor and can even damage the unit permanently. So we don't want that. Again, we need an anti-short cycle to prevent that. Now over here we have our terminal wires R, W, Y, O, and should be pressure switch and then commons all by itself at the very bottom down here. Pressure switch is coming out. So if we come here and we don't see the contactor pulling in, we check down there and we have pressure going on, what we can do is verify that we have a call for Y. So we would come from the Y terminal to a common and look for 24 volts. If 24 volts is present, then we're going to look a little bit further down and see what else may be going on. If we have 24 volts though and this contactor is not pulled in, we have to verify that it's getting the 24 volts out right here on the Y. So Y goes into the board, it goes through the pressure switches, then back out of the board. So our job would then be to come over and start pulling our pressure switches off and ohming them out, looking for continuity through the pressure switch. So we'll go ahead and do one right now. These switches should read closed. It's not the pressure switch. So these are going to be our high and low pressure switches. I've got them right now tied together in series. So we got one set. So if we read that, we know our pressure switch is closed and we should have 24 volts going into the pressure switch, out of the pressure switch. So we can come back down here to the board itself and also try to read 24 volts coming out of our board on the two pressure switch terminals. Between them, one of them, we should get 24 volts, and the other one we're going to have to read back to the common wire, and that's going to give us 24 volts as well, telling us that it's trying to read through. If we don't get anything there, the board itself may have malfunctioned. Back up real quick.
If it moves!
Now, sometimes pressure switches, they fault out. If it's a high pressure switch that open, it should automatically reset when the unit turns off. Once the unit quits running, the pressure should be able to come down below its high pressure point, which on this unit would be like 650 psi. So at ambient temperature, this 410A refrigerant should be sitting around 140 something psi. So it'll come down and it'll reset that switch. If it does not reset the high pressure switch, it's a simple answer. It's not a question of whether we still have high pressure. It's a question of, it's not even a question. It's the truth of the high pressure switch failed. So we have a failed high pressure switch, failed in the open position, and we need to change that out. So that would be located inside said unit. And we can take the high pressure switch and change it. Again, we already verified that there's not low pressure issue, but let's say the low pressure switch was open, and you've already verified there's 140 psi of refrigerant pressure on the unit. That should not be an open switch. That switch is bad. If you come here to this relay, or this contactor in this situation, and you check between this side and that side, and you've got 24 volts, and yet the contactor is not closing, but you know you've got 24 volts applied, you've got a bad contactor. One of the ways we can check that contactor you check the contactor for resistance. You're probably going to see somewhere around 12 to 14 ohms of resistance right at startup, maybe 18, depending on how much load this thing can take. It's got 13 ohms of resistance. That's a good contactor. If we get below 10, we're questioning our contactor. It may be our problem. And if you go too far above 20, your resistance may be too high. You may have the wrong coil. That happens sometimes too. If you're behind another guy or another technician and the unit hasn't ran since they left, come down to the side of the coil, read 24 volts. If it doesn't say 24, if it says 120 or 240 on it, they put the wrong coil in it. We only have 24 volts supplied by our transformer we saw inside. If that resistance is too high, we don't have enough juice to make that coil energize and close the contact points. So our electromagnet inside that relay is not working. Like I said, it's anywhere 10 to 24, 10 to 20, I'm sorry, ohms of resistance. Anything outside of that too low, you may actually end up with a short and pop your fuse. Too high, you don't have the juice to pull it in. So we're going to come across here, verify that we have 24 volts. Let's say we do have 24 volts. This looks like it's pulled in, but you still read line voltage across the top when you go across it. If you still read line voltage, then that means there's something going on here in the plunger area. It may be pulling in, it may look closed, but it could have some type of debris, a bug, or something stuck between the contact points. And it's our job to identify if that's the case, or something that's going to make you change this contactor out. If the points have splattered to the point where they no longer make contact, that can happen as well. And it's time to change that contactor out anyways. And it's also time to figure out what the heck made that contactor fluctuate so much that it splattered the points. It should not. It's a definite purpose contactor. It receives 24 volts. It should be a solid closed and solid open. Usually if you see splattering on the contactor points, it means it did this. At some point, it may have had just a quick on and off, but you're trying to bring on a condenser fan and a compressor with that, so it's going to spark and weld and arc and create new problems. It may not weld, but it will arc. Sometimes, though, you will find one leg welded shut, and it'll just kind of run constantly on one leg of power, which is also a big issue for the rest of the unit. But when we look at these defrost boards, don't let them freak you out. There's a lot of resistors. There's a lot of relays inside of it, but it only serves two functions. It has a time delay, and it has a defrost control. Everything else is controlled by other switches inside the unit. So this thing only does two things. That being said, in defrost, one of the things that could happen, and you'll find this more in the spring, but let's say the unit malfunctioned during the defrost cycle, the board quit working. Customers didn't notice because they had electric heat inside, supplemental heat. They stayed comfortable throughout the winter months. Here you are in the early spring. It's our first day that bumps above 75, 77 degrees, high humidity. Customer says they're uncomfortable. You come out, that one's not happy. AC's running. Turn that off a minute. The AC's running and everything, but the fan's not on. Well, that doesn't always guarantee a fan motor failure. That can sometimes just be an issue between the two components here. This DF1 and DF2. This is what powers the fan. And because this defrost board went into defrost multiple times this year, it could just be careful. I think that one's missing some safeties on it. Yeah. It's the fan, huh? Yeah, we'll have to tighten that bad boy back up. I heard that. All right. So, we may find that the defrost board went into defrost, and while it was in its defrost cycle, it failed to close this switchback that connects these two wires. One of the ways you can easily find out if you're here, and that's the problem, you can take this fan run wire, identify where the other side goes on the defrost board, take this fan run wire and put it right here, make the contactor engage, and if the fan runs, fan's good, defrost board is good. This is called a fan out here, by the way. I know that we have it kind of inside on and off saying fan blower, fan blower. That's because thermostats say fan, but text says blower. So again, if this contactor didn't pull in, you got to check your pressure switches and verify 24 volts is getting to the contactor. If this fan doesn't come on, you need to check, kind of like we talked about earlier. You can come to your capacitor, you check your fan terminal on your fan. But you're also going to look right here. This is very common, that the DF1 to DF2 switch stays open and will not allow it to energize, causing it to have a problem with voltage getting to the fan motor and making it run. After that, let's say that this is good, power is on, fan's trying to run, fan's smoking hot. You touched it, it's really hot. The dual run capacitor is probably your problem. And with the dual run capacitor, just like we had before, we're going to come to it. I recommend for you to go ahead and write down the wires whenever you're doing this. If you do them enough, you should know where they go. If you can follow a schematic, which if you take our class, you can. So we're going to come here and we're going to go from this common terminal to the fan terminal. And we're going to turn this back to microfarads. And on this one, we should be reading 5 microfarads, which we're reading exactly 5. And then let's say for some reason the compressor is not running, but everything's correct, power's on, trying to run, but it just doesn't come on. You're going to come from here to here. And this one wants to read 40 microfarads, and we're at 38, plus or minus 10, still puts us in range. This one actually says plus or minus 5, so we'll use theirs. That puts us out of range. It's 5% of 40 is 2. We're 38. We're literally right outside of range. So this capacitor could feasibly be changed. Now the company that I used to work at, they used to use the number 10%. Regardless of what the capacitor said, they looked at their customer and said, well, we know the fan will run all the way until we're below 10%. And should the customer have to pay extra money for something that's not really messed up? And the answer to us was no. So we used a higher value, 10%, and that 10% would just guarantee to the customer that, hey, listen, you know, we're trying to do our best of taking care of your issue without charging you an arm and a leg, but not everybody's like that today. So they want you to read the value stated on the capacitor. Now that sells a lot of capacitors, but again, that means your customers are spending a lot of money. And as a technician, you're a tradesperson. So that means that your craft is what you owe your service to, what you really need to pay attention to, not the company you work for. So who makes the money? The customer pays the company. Company doesn't pay anybody. It just gets money from the customer based on your craft skill. So if you lose customers because you make decisions to charge them more where you shouldn't, just go ahead and understand that you're losing your money over the long haul. So while it may make you money today, 20 years from now, that customer may not be using that company anymore and you may not have a job for them. So we like to use some other kind of rules, and those rules are considered, you know, a trades professional. You are an advocate for the customer as well as a representative of the company you work for. So you have to walk a tight line between verifying and making sure that you're getting the best deal and best service for your customer, but at the same time providing an adequate speed so that it doesn't cost your company much for you to perform your services.